Good afternoon, everybody, and welcome to this joint workshop between the eLECTRO Plastics to Olefins and Plastis project. We will start with the presentation on the eLECTRO project by Professor Kevin Van Geem. He is full professor at the Laboratory for Chemical Technology at Ghent University, and as said, he is a coordinator of the eLECTRO project. He is a former Fulbright research scholar of MIT. He directs the pilot plant for steam cracking and pyrolysis, and he was recently awarded with both an ERC Advanced and Proof of Concept grants. Thermochemical reaction engineering in general, and in particular the transition from fossil to renewable resources, are his main research interests. So Kevin will give you an introduction to eLECTRO.
Okay, good. So I will, of course, start with the eLECTRO project. And eLECTRO project has 4 objectives, so you can see them on the slide. But as eLECTRO says it itself, it's electrification. So with this electrification, with renewable electricity, we hope to reduce 90% of our emissions. And emissions are basically related to the benchmark, which is steam cracking. Steam cracking of naphtha, that's our benchmark process. And to do that, we will use plastic waste. We will convert that via pyrolysis and transform that into a liquid. And that liquid will be fed to a steam cracker. And on the steam cracking side, we basically have conventional technology that will benchmark with completely new technology, which is the rotordynamic reactor. And that's an electrified steam cracking technology which we will use in this process. And this is what we try to integrate. So we enable electrification, reducing 90% of our emissions, and of course, high-value olefin production. Who is eLECTRO? So eLECTRO has 12 partners, and you can see them on the slide. A lot of them are based in Belgium, like Ghent University, AFGI, Engie Laborelec, Prime half with their research, and but they're also in the Netherlands. We have Colebrook, which is also in the Netherlands, but also in Finland. ISTEng, which is in Luxembourg. Borealis from Austria, but also Finland. So we have a quite big Finnish connection, directly or indirectly. We have Polytechnic de Milan. We have our campus in Korea. And then we have also Aristotle University. And I forgot, Benkei, Jean, I will not forget you. What do we try to do? We have 7 work packages, but these are the 4 technical ones. And the first one is really on the electrified conversion of plastic waste, characterizing the waste, characterizing pyrolysis oils, cracking different feeds. The second one is basically the conventional steam cracking of those pyrolysis oils and all the challenges with contaminants, creating sort of benchmark, but also optimal integration strategies in existing steam crackers. The third one is then the RDR. So Colebrook's technology, we demonstrated at TRL7, but also computational support on developing this reactor technology. And last but not least, we have the techno-economic aspects. We look at LCAs, but also socio-technical aspects, and we compare it and benchmark it to what we have done. So we have our value chain, and we will start with the extrusion part. So the extrusion part, we have VTT, who is working with their modics. And then we go to the pyrolysis and steam cracking. And of course, there we have the optimization, which is mostly done by AFGI and Borealis. And here we have the electrification of the whole system. The downstream side is also covered by Borealis. Of course, they have a lot of experience in this area. And what is, I think, really crucial is that demonstration. And that also makes the project quite unique. We have really TRL7 demonstration, high skills, both at Colebrook and at Prime in Rotterdam. And of course, this allows to validate our models, but also to give suggestions for improvements. You see here all the companies that are involved, and you see them positioned at multiple places. So for the first part is the feed treatment. So we have there the extruder. I think you have seen the Modex and you see the products before and after being treated by the Modex, and those are basically then fed to our next step. And our next step, we have the pyrolysis, and I will hand over here to Dominique, who will explain you also the movie that we have for the prime unit. So here we have a TRL7 unit based in Rotterdam that also, well, we have a pilot unit also in Ghent, which is a small version of that one. And this allows us to reproduce at large scale, but also smaller scale, the quantities that we need both for pilot and for the TRL7 unit for Colbrook, for example.
So yeah, here you see some movie of our TRL7 unit in Rotterdam. So it was constructed and commissioned in 2024, early 2024. So we have operated the plant since about 2.5 years. The plant is designed for a nameplate capacity of about 26 kTA of mixed plastic waste. And the uniqueness of our process is that it is completely electrified. So mainly the pyrolysis reactor, the big energy consumer. So we actually start with our feedstock. We strategically have chosen not to invest in any feedstock shredding or pre-treatment technology. So we buy our feedstock from feedstock suppliers in the market, which supply it in the quality which we need. And at this moment in time where pyrolysis is at, there is sufficient feedstock available for us to acquire that from suppliers. That feedstock is then, when it arrives at our plant, it is unloaded and stored, how you can see it here, in a densified pellet or agglomerated shape. We can treat different formats of feedstocks, but it has to be able to be fed in our extruder, because after our feedstock storage, the feedstock goes to our extrusion section. So we have demonstrated on industrial scale 2 different extruder technologies, both a single screw and a twin screw extruder. And we have been able to show that we can effectively, let's say, transfer that mixed plastic waste into a homogeneous melt in temperatures of excess of 300 degrees centigrade. Here you see some pictures of our extruder building. Within the front, it's a single screw extruder. And in the back, we have a twin screw extruder. We also have the ability in the extrusion section to do some impurity removal, both moisture which might be still left on the feedstock and also some other impurities such as halogen removal can be done with the extruders. This is a piece of the hardened melt when it came out of the extruder after the commissioning, but in the end, the extruder will then feed from the outlet of the extruder the molten plastic at temperatures excess of 300 degrees to our electrified reactor. So we have a horizontal agitated reactor where we use multiple electrical heating circuits to heat up the wall of the reactor and conduct the heat transfer up until we have the cracking conditions for the polymer. The pyrolysis gas will then further go to the condensation section where we actually are producing the oils. As a byproduct of the pyrolysis reaction, we of course have the solid residues, or what we call the char. That char is actually dumped and cooled. First, it is actually dried and then it's cooled and we put it in big bags. At this moment in time, we do not yet have a circular product solution for that, so we actually dispose it as a waste. The pyrolysis gas further is then condensed in a multi-stage condensation section on our premises, and to actually receive the oil quality which we would need. We have some but limited upgrading steps afterwards when the oil is condensed, and then the oil is stored, what you saw actually in the beginning, in our tank farm, which are reconverted ISO containers, which we use for our tank storage. Then we actually use external lab surveyors, and of course some of the oil is also analyzed here by the consortium with the help of UGen, but we also use external surveyors to then analyze the oil and send then the oil to our steam cracking customers, which after upgrading is then in a diluted form used to produce new monomers. The The non-condensable gases at this moment, because we have electrified technology, we do not use them to combust and fuel the reactor. At this moment, we combust them in a thermal oxidizer. But of course, this is mainly linked to the demonstration, because in future projects, depending on where those would be built, we will try to integrate and valorize that stream in a better way. And further, I think the link very important also, as Kevin already hinted, we also have a TRL5 unit in Ghent, linked to LCT, and we use that mainly for screening of different feedstocks, where we can do a smaller trial to look at acceptance of quality before we use it in larger quantities here on the plant. And also, of course, for optimization and certain testing with catalysts or with other technology improvements. So that is the view of the TRL7 unit. So thank you.
Thank you, Dominique. So then we are at the RDR, so basically the electrified cracking. So you can see it here. I've built it already twice, this unit. We also have a movie about it. But you can see that what we did was we were able to demonstrate not only naphtha cracking or a combination of pie oil and naphtha, but really 100% pie oil cracking in this RDR unit. And so reducing both scope 1, scope 2, and scope 3 emissions in this way. And this is heavily supported by very advanced modeling. So one of our people here, Mike, I think he uses a lot of supercomputer capacity in this respect, supported by Tamas and people from AFGIF on the kinetic modeling. So very advanced modeling supporting the RDR development and helping to further improve it. And I think thanks to the product also we made substantial steps in that part. So really 3D simulations, advanced CFD, together with detailed chemistry.
What is Coolbrook doing and why is it important?
Coolbrook are trying to decarbonise heavy industry, and it's the high temperature, high thermal power stuff that at the moment there's very little you can do other than burning stuff. It's really hard to do anything else, but we've got the magic answer that solves that.
This is a research campus where a lot of research is taking place in chemicals and materials. And it's actually part of the chemical site where there is a big petrochemical production, which indeed exists for over decades.
And also, it used to be, from what I understand, a coal plant, and it's kind of gone through various iterations. Sort of makes sense that it's paving the way for the clean energy transition.
Absolutely. We have done a couple of transitions from this area, and now we're looking at the new energy transition. And this is a great place to facilitate that and to bring the technology to the next level.
The petrochemical site in question is Camelot in South Limburg, and we're just next door on the Brightlands Camelot campus, an open innovation hub where scientists and startups are moving chemistry beyond fossil fuels and towards circular and bio-based materials. Which is why Coolbrook is here to test its pioneering rotodynamic reactor. They are testing it on one of the most energy-hungry processes in the chemical industry, steam cracking. Traditionally, this relies on gas-fired furnaces to heat naphtha until it breaks apart. And Coolbrook does the same job using pure electricity, heating the material to around 1,000 degrees Celsius in milliseconds. That heat cracks molecules into ethylene and propylene, the building blocks of plastics. By electrifying the process, Coolbrook removes combustion emissions and increases yields with more precise heating. Ultimately, the goal is to move beyond virgin plastic, and Coolbrook has also proven the process on pyrolysis oil made from waste plastic, turning it back into new feedstock. Now, Coolbrook aren't just focused on steam cracking, but it is an interesting case study as an industry so ripe for electrification, using vast amounts of energy and, critically, armed with the scale and capital to change. So it's more efficient, but how does it actually work? This is what's generating the temperature in there. Or rather, this is a scale model of what's going on in there. And what we can see is a cross-section of the rotodynamic reactor. It would be the same cross-section also for the rotodynamic heater. And it is a turbo machine, and turbo machines transfer energy between a rotor and a working fluid like gas or liquid. And typically we see these to generate thrust in, say, a jet engine or to generate electricity in a gas or steam turbine. And they work because of the relationship between pressure, volume and temperature. PV equals nRT, the ideal gas law. Squeeze a gas and its temperature will increase, let it expand and it will cool. Physicists have been exploiting this for decades in order to optimize these turbo machines. Now let's take, for example, a jet engine. The idea is to compress a gas, making it ripe for combustion. But along the way, as it passes through stators and rotors in order to do so, it needs to limit temperature increases and limit the amount of entropy or inefficiency that's introduced to that process. Physicists want that process to be as reversible and as adiabatic as possible. Now with Coolbrook, the principle is the same, but the objective is totally different. Here, we want to increase temperature and increase entropy in order to do so. So here's how it works. We have our preheated gas, which passes over these stator blades. An electric motor is spinning our rotor at super high speeds. This accelerates the flow where it hits the diffuser and is going so fast it creates a shockwave. That shockwave has a tremendous amount of energy and has nowhere to go, so it collapses into heat, heating our gas within milliseconds to up to 1700 degrees C. That gas then travels around this sort of toroidal shape and goes through these stator-rotor-stator blades multiple times. It eventually exits here, but it does have the effect of meaning that this is a very dense system, meaning that it's essentially plug and play, replacing what might be a huge furnace with a much smaller system. So very efficient on that front too.
So here you can see the, the unit. See also the impressive measurements that are there. There's also a unit which basically provides a lot of validation data for the eLECTRO project. And then we are at more than the downstream and so on. You see that well, the products that we produce, they have to be also converted back to polymers. And this means if you introduce pyrolysis oils, they are contaminated. This means that the ethylene and propylene needs to have the right purity to reach that. So with the help of Borealis, we are able to address those topics and to further optimize and develop ideal techniques to use the feedstock in a much more efficient way.
The mass balance model. It works by partially replacing fossil feedstock with renewably sourced feedstock. It allows us to make ISCC certified sustainable polyolefins without reducing quality or safety standards, all while minimizing CO2 emissions.
Hi, I'm Stefan Roest. I work at Borealis at our Circular Economy Solutions team, and today I'm going to explain you a little bit about mass balance. For our circular solutions, we are using mass balance to feed sustainable or circular feedstocks in our production assets. And today I'm going to explain you how that actually works. So what I have here is a big bowl which represents our production facility and is already filled with white pellets which represent fossil feedstock. And I have these green pellets which represent the sustainable or circular feedstock. We need to make sure it is compliant to the same quality standards as we have for the fossil feedstock. So we do that by, for example, using renewable naphtha instead of fossil naphtha, or in case of chemical recycling, we are upgrading the chemical recycling oil to a level that we can feed it into the production facilities. Those quality checks are also helpful because it means that all the products that are produced afterwards are at the same quality as the conventional products. So they really are drop-in solutions. So they can replace the existing grade just when using a different feedstock. So that's very beneficial also for our customers because then they don't need to do requalification or quality checks on those products again. So now let's get started. What we first do is get rid of a part of the fossil feedstock that we don't need. So I'm getting that out of this bowl like this, and then I'm adding the sustainable or circular feedstock in like this, and then I'm starting to mix that, and then what you see is that it is completely mixed, and we are filling one bowl with a grade, so this is a product, a plastic with the sustainable feedstock, and then this is a product or a plastic with the conventional feedstock. So here you see they actually contain the similar amount of, or quite similar amount of sustainable feedstock and fossil feedstock, but only one we can sell as circular. The other one we just have to sell as fossil, because only this amount of sustainable feedstock we have put in, and according to the mass balance, this is also the amount of product or feedstock that we can allocate to the final product. For this we need a certification. So what we do is we have ISCC Plus certification, which is actually checking this whole mass balance system for us, but also in the rest of the value chain. So in that way we get traceability of these feedstocks all the way from the beginning of the value chain, as well meeting certain sustainability requirements that ISCC Plus is setting and checking throughout that chain. So to conclude, we can already use our existing production facilities to start using these sustainable feedstock in those facilities, cost effective, integrated. As well, we avoid that we have to build a parallel new value chain to start with these sustainable feedstocks. As well, by using the mass balance approach and those existing facilities, we are already pushing out the fossil feedstock in the same assets. So in that way, we are gradually transitioning to a fully circular economy. And in this way, we can start the transition to a circular economy today. I hope this example was clear. I hope to see you next time. Thanks for watching. Bye-bye.
If you look at impact, several of us were involved in this legislation, but also if we look at our numbers, then we see that we can drastically reduce the CO2 footprint of the process. We get over 85% reduction compared to the state of the art, but if we really focus only on the naphtha steam cracking, we're above 90%. If you, of course, use renewable electricity. And obviously, we did sensitivity analysis to identify the main emission sources and to get it further down as well. So all these things will be published in high impact journals together with all the partners, both industry and academic partners that you see on this slide.